Hello and welcome to this REBOUND YouTube tutorial. My name is Hanno Rein and today I'll talk to you about how to add particles to a rebound simulation. We'll first be talking about how the coordinate system in rebound works, then we'll talk a bit about orbital elements, and then I'll show you how to interface with the NASA JPL Horizons system. So let's start with the Cartesian coordinates and how to add a particle using this in rebound. We first import rebound into our Python notebook. Then we create a simulation. And now we can add particles with the sim.add syntax. Here we add a particle to the origin with mass m equals 1. We can add more particles by just repeating the process. For example, we can add a Jupiter mass planet at a position of x equals 1 with a velocity in the y direction of 1. This roughly corresponds to a circular orbit with a semi-major axis of 1. And that's really all there is to adding particles using Cartesian coordinates in rebound. If a coordinate is not specified, then it is assumed to be 0. Same is true for the mass. If we add a particle and we don't specify the mass is assumed to be 0 and we have a test particle. Now it's important to know that the internal coordinate frame that rebound uses is an inertial frame. It assumes that you have an inertial frame. You might remember from your undergraduate physics class that an inertial frame is a frame of reference that is not undergoing acceleration. And that is a convenient frame to use because Newton's law apply in this frame. Other n-body integrators sometimes use a non-inertial frame, and that can lead to some confusion. Why would one use a non-inertial frame? Well, a heliocentric frame is a natural choice if one's working in the solar system, where one is mostly concerned about the motion of particles around a central object. However, that is somewhat limiting, and rebound is giving you more flexibility by offering you to work in any inertial frame that you wish. However, this inertial frame also comes with some potential pitfalls. Most importantly, the following. Particles might drift away from the coordinate origin. Even if you add particles at the origin or close to the origin, sometime later they might be quite far away from the origin. And even a slow drift can be significant after billions of orbits. Why? Well, because of the finite precision of floating point numbers. There are only about 16 decimal digits available to represent a position using double floating point precision. So if your particles are very far away from the origin, then their relative coordinates cannot be calculated very accurately, and that can lead to the loss of precision, or in the worst case, the integrator can fail to converge. The solution to this is to work in the center of mass frame, and I'll show you this issue now. So if we take this simulation that we've just created and simply integrate it forward in time, for let's say 10,000 time units, and then output the coordinates of the particles, you'll see that this central object has an x position that is no longer at the origin and is actually quite far away at 0.01. More importantly, the y position is also no longer at 0 and is now at almost 10. And this is because the center of mass was not addressed in the initial simulation. We can check this by calculating the center of mass and printing out the x, y, z positions. You can see the x, y, z positions are 0.001 and about 10. And this is because if we calculate the center of mass again, now put the velocities. The velocity of the center of mass is non-zero in the y direction. The easy fix for that is to simply move the simulation to the center of mass frame, and there's the method move to COM that does precisely that. After that, you can calculate the center of mass again, both the position and the velocities, and you see that they are exactly equal to 0 within machine precision. Don't worry about the small numbers 10 to the minus 19 or 10 to the minus 15. For all practical purposes, these numbers are 0. So if the center of mass is initially at the origin and you don't apply an external force, then the center of mass will remain at the origin for the duration of this simulation. Next up, let's talk about orbital elements. REBOUND allows you to add particles in many different formats, and orbital elements are a feature that you might often use. So let's create a new simulation for that. And once again, let's add a central object with a mass of 1 at the origin. If you're wondering about the units, I refer to you to later video that explains the units used in REBOUND in some more details. So we can now add additional particles using orbital elements. For example, we can add a particle with a semi-major axis of 1. We haven't specified any mass, so it assumes that the mass is 0. We can also add more orbital parameters and be more specific about what we want. The previous orbit was on a circular orbit because we didn't specify the eccentricity and it assumed a circular orbit by default. We can also add an eccentric orbit, for example, like this. You can add up to 6 orbital elements when you initialize a particle. For example, a semi-major axis, an eccentricity, and then various angles, such as the phase of the orbit, the orientation of the periastron, the inclination of the system, and the orientation of the ascending node. If you add more than 6 parameters or some combination of parameters that doesn't work, REBOUND will give you an error message. These 6 parameters that I've given you here are only an example, and I refer you to the documentation to look at all the available options. Let's have a look at the particles we've just added. We can look at the Cartesian coordinates that we have gotten from those orbital elements by using sim.status, because internally REBOUND always converts these orbital parameters to Cartesian coordinates. We can also quickly make a visualization of how these orbits look like using rebound.orbitplot. And then we get an image out showing precisely those 3 orbits that we've just added. If you want to have a 3D view, you can get 3D slices and look at the orbits from different directions. You see that the outer orbit is indeed inclined with respect to the other orbits that we've added. So this is how you add the particles using orbital elements in REBOUND. An important feature of REBOUND is that it's using Jacobi coordinates when you're adding particles in orbital elements. Jacobi coordinates can be confusing, which is why I'll explain to you in a bit more detail what is happening here. Orbital elements are only really defined for 2 bodies, a central object and a secondary, for example, a star and a planet, like shown here. Then the semi-major axis can refer to the distance between those 2 objects. However, if you add more than 2 particles to a simulation, then this becomes not so unique anymore. Imagine the second planet here. Is the second planet orbiting the star, or is the second planet orbiting both interior objects, the planet and the star? If you assume heliocentric coordinates, then you just ignore this inner planet, and the outer planet is simply orbiting the star. If you use Jacobi coordinates, then the outer planet is orbiting the center of mass consisting of the star and the inner planet. REBOUND is using the Jacobi coordinate system by default. So from that perspective, the outer planet only sees one object in the center, the primary object consisting of the planet and the star being combined at their center of mass. Let me show you how this can lead to some potential pitfalls. It's especially important to remember that the order in which particles are added matters. You need to add the particles from the inside out, starting with the central object, then the innermost planet, then the second innermost planet, and so on. If you don't do that, then these Jacobi coordinates don't make much sense. I'll show you how that looks like in a notebook now. So in all those previous examples I've shown you, implicitly Jacobi coordinates were assumed. We don't have to do that. For example, let's create a new simulation. Once again, we add a central object at m with a mass of m equals 1 at the origin. And now we add another particle that has the same mass. So it's an equal mass binary on a circular orbit with a semi-major axis of 2. Now, if we were to add a new particle with a semi-major axis of, say, 0.1, REBOUND would assume that this is a circumbinary object. However, that might not be what we want. For example, we might want to specifically tell REBOUND that this is now a particle which has a primary as the first particle that we've added. You can do that saying primary equals to sim.particles 0. This then corresponds to this particle that we've added first. Similarly, if you calculate a orbital parameter using sim.particles, and then the particle that we've just added, and query the semi-major axis, you might get a value back that you do not expect. Here we get minus 0.75 as the semi-major axis for a particle that should have a semi-major axis of 0.1. What is going on here is that this line here implicitly assumes Jacobi coordinates. We can manually switch this over to have heliocentric coordinates by manually calculating the orbit. So we say sim.particles to calculate orbit, and then we specify which primary we want to use. Here, sim.particles 0. Then we get an orbit object back, of which we can query the semi-major axis. And this time we get the semi-major axis of 0.1 back, which is what we initially put in. So keep those Jacobi coordinate convention in mind. It can be confusing, but it is very useful whenever you're working with binaries or planetary systems in general. Last, let's talk about NASA JPL Horizons. You might already be familiar with the NASA Horizons system. This is a database that you can query for the location of many celestial objects, including many spacecrafts, at any time from any position in the solar system. This is used to calculate trajectories of spacecraft and many other things. You can also interface with this Horizon system directly from REBOUND. Let me show you how that works. We once again create a new simulation to have a fresh start. And then we just add particles by name. If you say sim.add sun, REBOUND looks up a particle with the name sun in NASA Horizons, finds it and then adds it to the simulation. We can go on and add other planets in the solar system. We can also add multiple planets at once, for example, Venus and Earth. Should take a second or so to create a database, and then it gives you a warning message in case it can't find the object. You can also look up the specific ID for objects in NASA Horizons and specify precisely which object you want in case the name is not clear. Let's plot those orbits that we've just downloaded. And you will see a representation of the solar system today. By default, whenever you query NASA Horizons from REBOUND, it assumes that you want the positions of the planets or other objects today. You can specify a different date. For example, we could add Mars where it was at a different date. For example, 2022, December 1st, 11 hours, 10 minutes and 9 seconds. This is in UTC time. This is all that you need to add any object in the solar system to REBOUND. If you want more information about how to add particles to Rebound, I encourage you to look at the documentation. There is a specific document just about how to add particles, summarizing what I've just discussed in this video. It also gives you the syntax for C in case you use the C version of Rebound. And then there is always the GitHub repository where you can post issues or questions that you might have with Rebound. Either myself or someone else will be happy to answer questions that you might have. Thank you for listening to this video and looking forward to seeing you in the future. Goodbye.